Hello everyone, thank you for attending this presentation. My name is Fernando Quintero Borbón from the Universidad Autónoma de Sinaloa and CIMAB Monterrey, and today I'm going to talk about this work named Optimization of Luminescence of Chloride Cesium and Lead Bromide perovskites synthesized by AACVD. Perovskites are materials that have a structure of ABX3. One kind of these perovskites are the halide perovskites. These materials are a great prospect for optoelectronic devices due to properties like tunable bandgap energy, low cost of fabrication, good electronic transport properties, and high optical absorption coefficients, among others. Here we have an AACVD that was used in the experiment, in which we start from two precursors that are chloride cesium in methanol and lead bromide in DMF. Those precursors are put in the nebulizers that transform the precursor into an aerosol to be dragged by nitrogen to the heat zone, where is the silicon oxide substrate at 150 Celsius, and the motors move through the substrate to form the thin films. The experimental set was chosen with the objective of studying the properties of this perovskite by AACVD and the goal of optimizing the luminescence of these materials. We have varied the molar ratio of chloride cesium with respect to lead bromide by fixing the lead bromide molarity at 0.05 molar. So our parameter is the chloride cesium molarity. In other words, we start from lead bromide thin film and start to add chloride cesium until we have the perovskite cesium, lead, bromide 2, and chloride. We expect something like this graph in the optimization of perovskite, where the sample lead bromide and the perovskite don't emit, but at some point between them, the luminescence is maximum. The characterization made were photoluminescence, transmittance, atomic force microscope, scanning electron microscope, X-ray diffraction, and X-ray photoelectron spectroscopy. In the photoluminescent results, we found that the maximum luminescence was on the sample M212, where the sample has two peaks of emission. The leading peak is in 2.555 electron volts due to the cesium lead bromide 2 chloride perovskite, and the second emission peak is in 2.45 electron volt due to the cesium lead bromide chlorine 2 perovskite. In transmittance, we found that the samples M2N2 and M2N3 have changed in the transmittance spectrum in 2.55 electron volts that correspond with the bandgap of the perovskite, meaning that those samples are in fact a perovskite. On the other hand, the samples that haven't changed in 3.3 electron volt, which correspond to the lead bromide bandgap, meaning that those samples are lead bromide thin films. This means that the samples that have more luminescence are the lead bromide thin films, but with support of the PL results, there are perovskite on the surface that is the cause of the luminescence. In the AFM results, we obtained that the sample coverage increased with the ratio of chlorine cesium and with respect to lead bromide ratio. Also, we obtained a high difference that goes up to the 2 micron in some of them. The result shows the presence of pinholes in the samples. For SEM analysis, we made surface analysis and cross-section. The surface analysis shows us that samples have grains of different sizes, and the size decreases as the chlorine cesium with respect to lead bromide ratio increases, going from 1.44 microns to 0.82 microns on average. The maximum grain size was found at 6.62 microns. In the cross-section analysis, we see two things. First, that the films are not uniform over the surface, and second, their thickness, which was around 600 or 700 on average. Also, the thickness increases with the chlorine cesium with respect to lead bromide ratio. In the X-ray diffractograms, we found peaks that correspond to lead bromide in the samples with low chlorine cesium lead bromide ratios, like the 002, 111, and 112. On the other hand, as the chlorine cesium lead bromide ratio increase, peaks as 100, 110, 200, 210, and 211 appears. Those correspond to the cubic and orthorhombic phases of the perovskite cesium lead bromide 2 chlorine perovskite. For the XPS results, we obtained the atomic relatives elemental compositions, where we had the cesium, lead, and chlorine tends to be 20%, and the bromine tends to be 40%. These results correspond to the ideal stoichiometric ratio of the perovskite ABX3, which are A x over B is equal to x over A equals to 3. In conclusion, the result of this investigation demonstrated that AACVD is a good alternative to synthesize good quality perovskite thin films with good reproducibility and uniformity. The luminescence of the perovskite thin films has been optimized by varying the molar ratio chlorine cesium lead bromide in the precursor solution. The maximum of luminescence was reached in the sample with the chlorine cesium lead bromide molar ratio of 2 over 12, where the main emission is at 2.55 electron volts, which correspond to the cyan color. Perovskite thin films of different crystal sizes up to 2 millimeters and thickness in the range of 600, 700 nanometers were found. And finally, this was my presentation of this work. Thank you.